The next few sections of this module are going to talk about more practical issues with a stochastic gradient, which you need to address if you're implementing those algorithms. I've made the next few sections optional because it can get really tedious to go through all these practical details. You now already got a sense of how finicky it can be. There's many other practical details. I'm going to make those sections optional. So the first one is that learning from one data point is just way too noisy. Usually you use a few data points. And this is called mini batches. So really we've illustrated two extremes so far. We illustrated gradient, where you make a full pass through the data and you use n data points for every update of your coefficients. And then we talked about stochastic gradient, where you look at just one data point when you're making updates on your coefficients. And the question is there something in between where you looked at b data points, say 100? And that's called mini batches. It reduces noise, increases stability, and it's the right thing to do. And 100 is a really good number to use, by the way. Here I'm showing the convergence paths on the same problem we've been looking at, but comparing batch size of 1 with batch size of 25. And here you observe two things. First, the batch size of 25 makes the convergence path smoother, which is a good thing. But the second thing to observe, which is even more interesting, is when you get around the optimum, batch size of 1 really oscillates around the optimum, while batch size of 25, it oscillates better. So it has better behavior around the optimal. And that better behavior is going to make it much easier to use this approach in practice. So mini batches is a great thing to do. So now we've introduced one more parameter to be tuned in this stochastic gradient algorithm. This is the batch size b. If it's too large, then it behaves just like gradient. For example, if you use batch size of n, it's exactly the gradient ascent algorithm. So in this case, the red line here is with batch size too large. If the batch size is too small, you have bad oscillation or bad behavior overall. So b too small. In this case, it doesn't converge very well. But if you pick the best batch size b, you have very nice behavior. You quickly get to a great solution and you stay around it. So picking the right batch size makes a big difference. So let's go back to our simple stochastic gradient algorithm and modify it to introduce the notion of batch sizes. So instead of looking one data point at a time, we're going to look at one batch at a time. And if the batch size is the size of b, we have n over b batch sizes for a data set of size n. So, if we have 1 billion data points and batch size 100, is 1 billion over 100 of those. And now we go batch by batch, but instead of considering one data point at a time in the computation of the gradient, we now consider the b data points in that mini batch. And the equation here just shows you the math behind basically the obvious thing of just taking 100 data points and use that to estimate the gradient instead of 1 or instead of 1 billion.